now we are going to start implementing all of the stuff that we explained, all of the objectives that we explained in the code. Okay, so I just copy pasted the simplified terms that we introduced in these slides here, just to have them as a reminder. And as you can see, we are going to compute this objective, and we're going to backprop through them, obviously. But one of the primary terms in this objective is computing the log-probs of the model. So basically, you want to compute the probability of generating a particular token at a particular time step, okay? And then you're going to multiply it by the advantage. But for now, we have to first compute the log-probs, okay?
Yeah.
And okay, let me get started. Before computing the log-probs, we have to obviously load the model. Let me use Hugging Face. We are going to Hugging Face transformers for the entire implementation.
But why can't we use vLLM?
vLLM, its model implementation is based on PyTorch, and it is based on PyTorch, but it is not really useful for us for training, basically. And the reason for that is many of these computations are based on some versions of customized CUDA kernels, and those CUDA kernels are, I think, customized for inference. It's not really useful for us to use the model that is inside the inference engine. And if you go even beyond this, sometimes your inference engines, they are not even in the same process, so they might be in different nodes, and so you don't have any access.
They don't even give you like differentiable logits, right?
I think in general it is like a PyTorch model. If you go and read the model implementation of Llama, for instance, in vLLM, there is a PyTorch implementation, and some part of it, like for instance the attention part, it is calling the CUDA kernels. So maybe in theory it is possible to do this, but for us it doesn't make that much sense, because
there's just no easy way, right?
There is no easy way,
not a hard way. Maybe if you want to go and be a vLLM engineer,
I think like on a slot it has like an implementation of GRPO that it shares the models inside the vLLM for training. But this is not the purpose of this talk.
Too much
this video really.
Complex,
yeah. Any case, let's get started with a good old Hugging Face. So from transformers, import auto model for causal, and yeah, I think that's what we need. And okay, let's instantiate the model. It is good old Hugging Face API. So we pass the model name, and there is this particular parameters that we can pass, attention implementation, and I think we can pass flash attention to. I hope this is the right parameter. And it also received the torch D type, which essentially says what kind of data type we are going to use for this model. And as we said for the vLLM, it is going to be float 16. And I think, and also there is this device map that you can pass. So essentially this tells the Hugging Face where to load this model. If you don't pass this, I think by default it loads it on CPU. But if you say device map equal to 0, or I think you can pass basically CUDA devices or any torch devices here, and it directly loads the model parameter inside GPU or any device that you specify. And in this case, it would be beneficial for us because it prevents us loading the model inside the GPU and then copying to inside the CPU and then copying to GPU.
Direct.
If you are low on CPU memory, this is a good option to try. So yeah, let's see if I have passed all of these things correctly. It seems so. It is starting to load the checkpoints. And yeah, let's see. Perfect. So we have the QN2 for causal LLM, and we have QN2 attention, and it seems everything is fine. Okay.
Perfect.
So we have loaded the model, and now just to make sure we the model is inside GPU. Yes, as you can see, it is good. Okay, so in the next few parts, I'm going to implement the part that we compute the Logprobs of tokens. And for that, I'm not going to use the episodes that we computed above. Just want to start with a very simple example and just to see how we work with Hugging-based models and how we extract or compute the Logprobs using this like transformer model. And after we finish this, we can just start using the episodes directly. Okay, so for the examples right now, I'm going to define this, and I'm going to use just very simple sequences. Word, and maybe how are you, and yes. So I'm going to pass padding to true because I want the tokenizer to do that padding for us, and this basically resembles a batch of two sequences. And what we're going to do next is basically try to compute the Logprobs on the language modeling task per se. But in sequence to sequence task, it's going to be a bit different, but I think the entire components are just the same. Okay.
So what does padding do? It just affects the, like it makes all of them the same lengths, right?
Yes. And I'm going to show you what it actually looks like. So we just ask it to return us the PyTorch tensors for this. Okay, so inputs, it's, let's see the keys. Okay, so we have input IDs and attention mask. So let's look at them. And input IDs, let's look at this. Yes, this is a tensor, like a 2D tensor of the input IDs of these two sequences tokenized. And let's just make sure, convert IDs to tokens. Just let's take a look at them, see how do they look like. So these are especially these particular tokens, okay? Okay. Okay, so this is our input IDs. Let me store it inside this variable. And let me show you the second one. If you are familiar with transformers, you can feel free to skip this part, but in any case, we are going to go over the entire thing. So we have the attention mask. What does attention mask says? The attention mask says that these two tokens are padded, just padding tokens. So the transformer model should not look at these tokens, and we should prevent ourselves from computing loss on these two padding tokens as well.
Just for the batch to have the same size.
Exactly.
And it's putting the end of sentence token right there.
If we look at here, tokenizer pad. So the pad token in this tokenizer, it is just saved as end of sentence, but
it shouldn't matter at all, right?
It shouldn't really matter, yes. We should be careful to not mask out actual end of sentence token IDs, but in any case. So again, let me also store this inside this variable. Okay, perfect. So we have constructed the input IDs, the attention mask. These are the input to the models. However, once you feed this to the model, it is going to create distribution over the next tokens for all of these inputs that you pass to it, right? And when you want to compute the loss, you have to have some sort of a labels to select which of these like vocabulary tokens you want to choose as your loss, right? When you want to compute the loss, okay? And generally, when you have a language modeling task or like causal language modeling task per se, your input IDs and labels are exactly the same because you have the same sequence as input and you want to just basically predict the next tokens of this sequence, okay? Let me construct the labels as well. So I'm gonna start with token IDs, with the input IDs, and let me clone them. Okay, haven't I defined it here? Okay. So we have constructed this. However, there is one problem here. And if you remember in like computing the input IDs, whenever there was a padding, tokenizer used this pad token, right, for this, or particularly pad token ID. Okay, this is the exact same one used here and here. Okay. However, when you want to pad the labels, you don't want to use the pad tokens per se. You want to use some other number. And the reason for that is basically we want to ignore them when we want to compute the loss, because it does not mean anything. So they should not really
You should
compute.
not predict them. And
Yeah,
you should not get a loss. They should not be included in the loss for sure.
Exactly. So the standard way to do this is to replace these pad tokens, or use minus 100 as the padding IDs for the labels. Okay, and by default, PyTorch cross entropy is configured to ignore these labels, but you can obviously change this minus 100. But in any case, we're going to follow the same format here. So basically, our label is going to be, let me define it here. Label is going to be torch where our attention mask is equal to 1. We are going to use the actual labels. Whenever it is not equal to 1, whenever we are in the padding regime, we are going to use minus 100. Let me compute this, and let's print it here. So as we can see, put the input IDs here. Okay, so just we can compare it. And it has just replaced these two with minus 100s. Okay.
If in this line we have used the input IDs equal the pad token, the problem would be we also masked out the end of sentence tokens.
Exactly, because our pad tokens is equal to end of sentence token. Exactly.
So it's a risky practice. They should have set.
It is a risky practice a bit if you are using input IDs equal to pad tokens. That's not a good thing to do. Always use attention mask. Any case, so right now we have this. Okay. So we have input IDs, attention mask, and labels. So these are the 3 ingredients for computing the Logprobs, and obviously the model itself. Okay.
And now the hard part.
The slightly harder part. Okay. So the way we compute the the Logprobs is we just first compute the logits, and then we compute the Logprobs. Okay, so now let's see how we compute logits. Computing logits is actually quite straightforward. So we just need to pass input IDs and attention mask. The model itself, it does not, when it is passing the output to you, when it is returning the output to you, it does not care about your labels. It is going to compute the distribution over next tokens. Okay, so it
for all of them.
For all of them. As expected, you are not going to pass labels as the input to the models.
You do pass the attention.
I think for Hugging Face models, if you pass the labels, it is going to also compute the loss by itself inside it.
Oh, I see.
So in the forward pass,
it gives you the loss as well.
Yes. Yeah, it's a kind of a convenient thing to do. But for us,
we're not going to use it. It's not spelled out.
Yes, right. Everything
is very black box.
Yeah, everything is nothing is going to be hidden.
Yeah.
So yeah, we are going to pass the input IDs, the attention mask, and there is this flag that if we turn it to true, it's going to return a dictionary to us. Otherwise, it just returns a
tuple.
A tuple, yeah, yes. Which is not really convenient to work with. And I think there is an option to enable cache. And generally, you do not need to pass this. This is used when during generation. But some model implementation, I remember like some versions of Mistral, it complained when cache was true, when cache was not false during training. So I'm just gonna pass it just to be sure and safe. So yes, let's compute this output. And I think obviously this is going to complain because our input IDs, they are not on CUDA. So let's make sure. And I think it should be fine. Okay, so we have the output. Okay, let me just put this out. So we have the logits and pass key values. This is the KB cache kind of thing. So because we are not generating, so we don't have to deal with this. And okay, so we want to work with logits, right? Output logits, perfect. So let's try to guess what is the shape of logits, right? So we pass the batch size of 2. So it's going to be batch size.
The size is 4, right?
Equal to 2.
Max.
And or sequence length.
Max sequence length?
Yes, let's use sequence length. It's, I think, from the context is obviously
clear.
And here is going to be the vocabulary size because it's computed on the entire distribution of next tokens. What is the vocab size of this model? Okay, let's see.
Quite large. It's 150. No, wait.
Yeah, exactly.
50,000.
Okay, so that's our guess, and hopefully you're right. Let's see. Perfect.
As always.
I guess you are not correct, right?
Because wait. Oh.
Yeah, there is I think in general the size of the embeddings, I think they are implemented to follow some to be multiply or something. Oh, I'm not sure whether this is the case.
Is this a yeah, maybe it's the power of 2. No, is it multiplication of the power of 2 maybe?
Maybe.
Because this one is odd at least, like the token size.
Yeah, what it means is that that last token is not going to be used. In any case, it's not about the last token. It's just so different, right? These two, like we have about like 300 difference.
So we were not as always.
As it turns out.
As it turns out. It is the first time. Okay.
Yeah. Okay, so we have these logits, and now it comes the part that's a bit tricky because we have to cut the logits and shift the labels. Okay, so what does this mean?
But why should you do that?
Why should you do that? Exactly. The reason for this is that we are doing next token prediction, right? We feed some token as an input or some context to the model. And for this particular token, the model's job is to predict the next one, okay? So as you remember, the input IDs and the labels, they were exactly the same. We created them to be exactly the same, besides the padding token, right? Obviously. So right now, when you feed the input IDs, you're gonna see the logits of this particular token, right? And you have to really shift your labels one to the right to see what is the next token for this time step. And we are going to use that next token, that shifted label, to compute the loss on this current time step.
That makes sense. Because the job of that logit is to carry the next token. So we need to move the tokens one step the left. The right. I mean, it's
yeah, one to the left.
So they are lined up with their logits.
Yes, exactly. If this part seems still confusing to you, don't worry. It's not super obvious in the first hand. So feel free to pause here and just go. I think there are many resources on Hugging Face on training sequence or causal language models. I think there are great resources on this particular topic.
There are great resources, but nothing comes close to this video. So just watch the rest.
Okay, so let's compute the shift labels. And it is going to be the labels that we have computed. And so the first part of the labels, let's have the labels that shape here. So the labels, they are going to have a shape of batch size and the sequence length, right? Okay, so we are not going to touch the batch dimensions, obviously. And we just need to shift one to the left. So it means that we have to start from 1.
Yeah, and we cut them. So it's like becomes sequence length minus 1.
Exactly. So you're basically starting from here.
Yes. Okay. Because the first token is never the target of prediction.
Yeah, you never predict the first token.
And it's always like the beginning of sentence token, right? So it doesn't even matter.
So yeah, we have this here. So one particular part that is remaining is to make it contiguous. And we do this so that when you want to compute the loss, it does not complain. Okay. So we expect this to be batch size, same batch size, and sequence length -1. Let's see. So if we compare it to the labels here, you can see it is starting from here, like from here exactly. And the size is obviously batch size times sequence length -1. Okay. So now it comes to the part that we have to cut the logits to the last, like the one before the last token.
Why do we do that? Because the last token, the last logit.
Generally, you can think of that as the last logit to be the logit for end of sentence token, and you do not want to generate anything after that, right?
Yeah.
So that one is.
But we don't have a target for it, right? I mean,
there is no
the last
target.
logit is trying to predict what comes next, but that thing is not generated. So
yes.
There's no target for it. You cannot calculate the loss.
Exactly. We call it shift logits because it's compatible with the rest of the variables here, but it's not really, we didn't really shift the logits per se. So we have the logits here, and we're just gonna have it until the element before the last, okay? And contiguous again, it's all obviously going to be sequence length -1. Oh, and obviously the vocab size that we miscalculated, misguessed. Yeah. Okay, so comparing this to this, you can see that it has a one fewer token. Okay, so one thing that I forgot is here. So generally when you take the logits out and you want to go ahead and compute the loss, it's a good practice if the memory is not a particular issue for you to use the 32-bit version of this, just to convert it to float, okay? And since we are in the oral realm, these data, right now I created this data here, but this data, it is coming from model's own generations, right? And the model's own generations, they are sampled from the model. And when you are sampling, you are using some temperature, right? In most of the cases, even in our case, it is a temperature of 1. But if you are using some other temperature, what it means is that you are multiplying this temperature by the pre-softmax values, and then you apply the softmax on top of this, right? So we have to divide these logits by the temperature. I'm not sure whether we have defined it somewhere, but for now, let's set it to be 1, and you divide it by the temperature. Okay, so this is going to be our logits. Perfect. So we are almost done. We have shifted our logits, we have shifted our labels, and we should be able to compute the Logprobs. So the next steps for this is to actually get the logits for any particular labels that we have for all of these time steps. However, if you remember, for the pad tokens in the labels, we have -100s, okay? And these -100s are going to be invalid because we don't have a token ID of -100, right? So we have to mask them out. So let's define the label mask variable here and set it to shift labels to be equal to, not equal to -1.
Right.
Perfect. So you can actually see it here. So this is our loss, sorry, our mask. And now it's the time to mask out these values, these -100s. So we can easily say shift labels, label mask. I think you should have used not, right? Sound good? So as you can see, these two that were previously -100, right now, these are different. Yeah, if you want to, we can compare this to these values, right? So these are exactly the same, but in the different direction.
The -100s
yeah, -100s are replaced with 0. Okay, so we are almost done. So we have to compute the Logprobs, they're going to be, first we need to, well, take the log softmax. Exactly. So generally you can apply the softmax and then take the log afterward, but there's if you use the numerically stable operation that we have here, so we just pass the shift logits and the dimension is going to be -1, so basically on the vocabulary dimension. Let's use dimension 2. I think this is more readable. Yeah. Okay, as you can see, we have computed the log softmax, and still we have not chosen the labels and just applied the log softmax, so to convert the logits to their particular log probabilities.
That's true.
Okay, now it's the time to get the actual Logprobs, and the operation that we are going to use is torch gather. So the way it works is that you pass the input that you want, and then you are going to pass the index that you want to choose from all of these, from this tensor particularly. So what we want is to take this from the dimension 2 or the vocabulary dimension, and we need to pass the index argument, and our index argument is going to be our labels.
Our labels. I think actually that's why we made those -100s to 0, right? Because we wanted to have a valid index.
Yes. So yeah, we wanted to have valid indices.
So it's going to get the log probability of the first token.
Yes.
The first token, yeah.
The first token.
Like the token 0.
Token 0. What do we know? What is token 0?
Is it the beginning of sentence?
I don't think so. I think this is the, I don't know.
Let's see.
Let's see.
Oh, is it the?
Yeah.
It's the probability of the exclamation mark. Interesting.
Yeah. I think this happens because when creating the tokenizers, this is the first
So
one.
if you see a lot of exclamation marks in your model's trained output, maybe you're forgetting to mask the labels. I don't know. At least if you're a Quen model, right?
If you don't mask out the Logprobs properly,
you're going to have more problems.
So expected all the tensor to be on the same device. Yes, exactly. This is not going to be correct. Shift labels, not the actual labels.
Interesting. What is on CPU? Our shift labels is on CPU?
Shouldn't be. Okay, yeah, we forgot to move it to the GPU. Okay.
Oh, I think that's the reason for the honest squeeze that we had. So you have to make it like a fake.
Yes.
Second dimension.
So yeah. This, as you see, these two inputs, like the input and the index that you want to use, they have to be of the same shape. So we have to use the honest squeeze. And I think let's take this out and okay. So I just want to return this and see how this looks like. So it's literally like the same tensor, just the shape has just changed. So if you can see, this has a fake. It's not a fake. It's a one dimension and third.
Yeah, it's just how torch gather works. It's a little bit cryptic.
Yeah, true. So we don't need to pass CUDA again. So it should be
and you don't take the honest squeeze, right?
Sorry?
Oh,
no, we didn't.
I see.
Sorry, in shift tables. Okay. So as you can see, we have the Logprobs and Logprobs, the shape. Yes, it is. Still, we have this kind of fake dimension. You can change it to use a squeeze to remove this.
Yeah, actually, let's take a look at the Logprobs. They should be very low for us because our model is not. Our input is actually fake.
True.
Not that low, but
It is a pre-trained model, so maybe
That's
these are
nice.
not. But these are generally like very small context. So generally, when you don't have a very large context, the model just it's not really certain on what to do. So I guess it should have low probability on all of the tokens, and
I
it means
see.
that you're gonna have very small Logprobs. Any case, we are not seeing that here, but these are not particularly
So
zero. So
we computed the Logprobs of our input IDs at the end, right?
yeah, I think I kind
Oh
of
yeah,
broke it. Yeah.
because you computed the squeeze twice.
Ah, yes. Yeah, let me redo this again.
Okay.
So, yes. And this is the last part that if you don't do, you're going to see a lot of exclamation marks. So now our like props, as you can see, these are masked and they do not
They are not
attribute.
differentiable. Right?
Yeah, they do not contribute anything to the grid. So yeah, just to summarize what we have done, it's a kind of a lengthy process to think about this, but just we started with the loading the model. We defined these variables and defined these input IDs, computed the labels, and we passed it to the model. We computed the logits. We do the shifting thing, and we just computed the log softmax or log props, and we use gather to select the proper valid label from the vocabulary distribution. And at the end, we have the like prop of generating this sequence from the model. Amazing.
Can we use our own function?
Actually, we have implemented this function here for just to be really like an easy thing to do. And all you need to do is to just pass the model, pass the inputs, and pass the temperature, and it should exactly give you the same thing that we computed above. Okay, let's use this utility function, and hopefully they are the same.
Oh, you don't want to copy paste it. But I think it assumes the deepest speed engine, no? Do they have the exact same API?
I think they have the same exact API. If you want to forward pass, they have the same exact API. Okay, so the output that we are going to have is the model and inputs. I think input IDs, we have to pass this. Attention mask and labels, but I just want to make sure that this labels is on the CUDA device because I probably forgot to do this for the labels, but I did this for input IDs and mask. And so we have this, and the temperature is equal to 1. So let's see, what do we see here? We see an error.
Still, oh, something is still.
Which one is this?
The input IDs maybe? Or attention mask?
I remember I put this to.
Oh.
Okay, I don't know why this happened. In any case, let's just
Call everything.
yeah.
Okay. Oh.
Oh, sorry. So here I made a mistake. This should not be.
Oh, the shift. I see.
Yeah. So as you can see, this is not an.
Not an easy task.
No, this is not a perfect video. So we learn as we go.
Yeah, that's true.
Okay, let's.
It's very. Oh, wait. We put it there because we've heard that if you put a mistake in the video, people are going to watch. Continue watching.
Anyway, I think it was painful for the viewers to see us make this mistake. Yeah.
Okay.
Okay, we computed the Logprobs, squeeze them back, and it should be the shift mask. Where is shift mask? Label mask. I think.
Should be, I see. It should be also computed to. Sorry, converted to.
this should work. Okay. So now we have the Logprobs, and it should be called. What is the label mask here?
Oh, why is it always true? I think like
Something happened here.
yeah, there is a.
What happened here?
We literally.
Okay.
And this should be
Label mask.
wait.
Oh, because we have already
Yeah.
changed this. Okay. Okay.
Okay, so it became a very educational video.
Very educational. You know what? We are going to load this from off the top, or just run this
just
from
from-
top. Yeah. Okay.
That's a problem with the Jupyter notebooks. It becomes state dependent. And
So yeah, these labels also on CUDA. Fit this in a model. Budgets. Shift labels. Shift logits, temperature. So minus 100. So this time, hopefully, label mask. Yes. Like softmax. Like props. Okay, perfect. Label mask again. We don't have to have it here. Here we go.
amazing. And finally, they are almost the same.
Almost equal.
I think, is it, why do you think like there is a small difference here? Is it the,
That's a good question.
the bfloat 16, like low precision maybe? Is it?
Yeah, maybe.
Or maybe it's just the order of.
Did we miss something? I don't think so.
The label mask. Yeah, I don't think so.
Let's compute this again.
I think it's just the. Yeah, I think it's just the order, maybe the thing inside. That is interesting because it's like the same code, right?
It seems so. So I don't know. Doesn't seem that this time we are going to find a. I don't think there's a bug here because there's just differences. But if in the edits we find it,
We're gonna
have another
come from future and
tell you what was the bug. But yeah, doesn't seem so. So coming back from
the future.
But the future is the next 2-3 minutes. We just found a bug, not the bug per se. So first of all, this should have been this one. But in any case, if you just use, you should have used float here.
Yeah. So our shift logits were just in bfloat 16, but in our own function it was float. So
it was float, yeah.
That was the reason for the discrepancy.
Yeah, and also I think it would have been like pretty painful for the viewers to see that I just use the normal logits, not the logits per.
Yeah. There is
not the shifted logits
pieces.
Any case, let's run this so that we can make sure that we are.
This time it's the same. Okay. They are the same.
Same.
I honestly think they should increase the accuracy of bfloat 16. Any case.
Okay, the previous section was a bit sketchy. It took several trials for us to completely finish it without any bugs. But fortunately, we have the utils right now. But I think at the end of the day, it showed you that the amount of details that we should really be really cautious about when implementing these kind of RL algorithms. And small things, as we saw, float 16, float 32, or different data types can also affect your probabilities, and obviously it might affect your optimization stabilities. I think it was a kind of a good showcase on these intricate details. In any case, so now that we have that utility function that gives us the Logprobs, we are going to implement the actual policy gradient loss. However, just before doing that, we need to do like one small step. And this small step basically is regarding the fact that in the previous step, we used a tokenizer to do the padding for us. But when you're going to implement the code, the episode generation is done by vLLM. And vLLM just returns the tokens, literal tokens. So we have to do the paddings and preparing of model inputs by ourselves. Okay. Right now, here we have a very small example on the output of episode generation. And we have 2 episodes from these queries. By the way, these are completely made up synthetic query token IDs and responses, right? And just wanted to mention that these 2 are the same as the format of our episode generation. It does not matter in preparing the model input, just wanted to show you the general structure of these episodes. Okay, so now the goal is to fill up this dictionary. So what is this dictionary? This dictionary is basically input IDs. We have to create this, and also attention mask. You have to fill this up. Labels. Okay, and we have to also create the advantages, do the paddings and all of those stuff for the advantages as well, because they're going to be used in policy gradient computation. Okay, so now that we have defined this, okay, so these are basic data preparation for model training. So these are, feel free to skip this section if you feel comfortable with this. Okay, so first I'm gonna compute the max length of the sequences of the entire episodes. So this is going to be the maximum of query and length of response. Previous example, when we implemented the computation of Logprobs from scratch, we used a simple kind of causal language modeling example. It was hello world and how are you? But here we have our sequences, they have 2 parts, the prompt and the response. Okay, so we need to combine these 2 together to create the input IDs and the entire sequence themselves. Okay, we have to loop over this to find the maximum sequence length. And, or as I said, the sequence here is the concatenation of query and the response. All response token IDs. Okay, so yes, as you can see, the maximum length is 11. And now that we have this maximum length, we can do the padding easily. So let's define the pad token ID just to have these 2 variables handy here. We're going to use the tokenizer pad token ID. And I'm going to also define another variable, ignore index, for the labels. So as I explained before, minus 100, these are the indices that we use to ignore the loss on the padding portion of the generation of the response of the model. Okay, now that these 2 are defined, we can safely go and continue with the filling of this inputs variable. Okay, let's loop over all of the episodes. Response, token IDs, and advantages. We have to zip over this. It's a bit lengthy, but is for a moment with us. Advantages, perfect. Okay, and let's put this think this is more readable. Okay, now we have to create our sequence, which is the combination of query token IDs and response token IDs. Okay, but I would like to also right now compute the number of padding that we have to do at the end of this. So just remember, we are doing the padding from the left in all of this entire train. So number of pads at end is going to be maximum length minus the length of combined IDs. Perfect. So from here, it's basically really easy to compute this. So the input IDs is going to be the combined IDs plus the pad token ID times number of pads at the end. Attention mask, it's going to be 1 for all of the combined IDs. It's the entire portion that the transformer can look at, times the length of combined IDs, plus, again, number of pad tokens at the end, and not the pad tokens, just 0. So for the portion that there is input, it's going to be 1. For the portion that we are padding, it's going to be 0. And for the labels, it's going to be a bit different, but not really. So the point here is that the labels, so all of these things, input IDs, attention mask, and labels, they're going to have the same shape, okay? But one difference in this case that we have here, where we have query and response, the difference between this case and the case that we had in the previous example, where we only had hello world and how are you, basically the causal language modeling, is that we are not going to compute the loss on the query portion. So we have to put the ignore indices for the portion that we have the query inside the labels variable. Okay, we're going to have the ignore index times the length of the query token IDs, or length of the query, plus, let me make this a bit easier to read. So this is the portion that you're going to ignore. This is not going to be contributing to our loss computation. And right now, we're going to add the response token IDs, the actual labels that we care about. And also the rest is the number of pads. They're going to be pads. And as we know, for the labels, we're going to pad them using ignore index. So again, number of pads at the end. Okay, this basically constitute padding and creation of all the model inputs that I showed before right now for our episodes. However, there is one last thing, which is the padding of the advantages. Creating advantages is very similar to labels. Advantages. Again, we are not going to have any advantage computed for the inputs. They are all for the response token IDs. So again, we don't have to use the ignore index here, because these advantages are going to be multiplied by the losses, by the Logprobs at different token at different time steps. Okay, so we don't have to use -100. We can just use 0 for the portion that we do not want to compute.
They are going to be ignored by the ignore index, right? They are not going to be multiplied. Like,
ignore index is going to be useful when we are going to collect the distribution of, we're going to collect the actual Logprobs from the entire distribution of vocabulary. So when the model computes the distribution over the entire inputs, entire vocabulary for a particular time step, when we use -100, we know that this part is going to be ignored. So this is particularly useful for that point, but obviously it is possible for us to compute the kind of the masking from these -100s for advantages. But
yeah.
So anyway,
I think like in W&B implementation, instead of 0, we put a very large number. So if in case by bug we were including that in computation, it would show up.
Yes, that's actually a good point. Yeah, let's put a very large number here, so that they're going to, it surely should blow up the computation if we were going to use this. But
yeah, it looks a little bit ugly in code, but
yeah, it's good to have these kind of
sanity checks.
Yeah. And yeah, advantages plus, again, this beautiful thing, times number of paths at the end. Okay? So the output of this is going to be a little bit ugly, but in any case, I think this is a good practice. So right now that we have all of these things computed, let's add them to the final, like the output variable. Okay, and now finally the labels. Let's not forget the advantages. Okay. Okay, so it is now computed. So if we look at the input IDs for the first example, we can see this. This is, let me copy paste this here again so that we can compare it easily. And yes, so as you can see, we have 12, 38, and 28 here. And the rest is just all of the response token IDs. And since this was the largest sequence in this entire batch, this is not going to be path. But if we look at the second one, we are going to see that the rest of it is going to be path tokens. And just remember that the responses are up to this part. It would have been better for this example if we changed this part
Yeah.
so that these are not equal to each other, but in any case. And so yes, we have computed this. Let's look at the labels. And yes, as we can see, 12, 38, and 28, these three are ignored in computation of labels, and we have 3 path tokens at the end. You can kind of find it from here. And yes, let's look at the attention mask. It should be similar to input IDs. So there is nothing here at the input at the beginning of this, or all of the padding is just happening at the end. Looking at the advantages, Yes. So the first 3, similar to labels, they should be ignored. And the last 3 are also the path advantages, and these are going to be ignored as well.
So let's compare it to the function in the code, right?
Yes. One last thing before completing this section. These are right now Python lists, so you have to convert them to
Torch.
Yes, Torch tensors. So this is going to be actually quite easy to do. Okay, so yes, we have them. We can take a look at the input IDs really quickly. Yes, as we can see, the padding happening here, labels, attention mask, and advantages. So yes, everything seems to check out.
So do you think it's better to compute the loss as in high precision? Is it possible to do it in vFloat16 calculations?
I think I know that we convert the logits to the full precision, 32 bits, when we want to compute the props. So it means that the entire computation of logarithms, softmax, and obviously all of the backpropagation from here to the model logits, they're going to be computed in FE32. I think doing this, it's going to be useful for the numerical stability of logarithms and so on, but I don't think it per se affect the logits of the model.
Because I was thinking the huge number we put in advantages may cause problems for vFloat16 if they were cast to vFloat16.
It's for float 16 maybe. I don't think this is out of is it the out of range? Yes, I think this is out of range for float 16. But for vFloat 16, the range is exactly similar to FE32, so it should not affect it. But let's make it compatible to FE32. I guess 10,000 is a reasonable number. F16, yeah. Yeah, let's look at this exact same function for when we have implemented this in the util. So there is this utility function that exactly take the query token IDs, response token IDs, and advantages. They are lists of leads. Basically, this is the episode, right? And in addition, it is also inputting receiving the device that you want to create these tensors. And the rest is exactly like what we have done in the Jupyter notebook. So we define the max sequence length and we loop over this, create combined IDs, and we create the path at the end. And we also have a couple of kind of sanity checks. So all of this should have the same length. And at the end, we are converting them to tensor. Yeah. And one more thing, I don't think this would be necessary for us. Yeah, because I'm not sure what would be the effect of this. I think if let's take a look at the data type of these tensors. Yes, this is already so yes, all of these things, the data types are as expected. However, here we just put it
explicitly, right?
Just to make sure that we are explicit about the data types that we are. But in effect, these do not really change these tensor types.
Can we compare them?
Sure. It's important to just see if it works. Prepare model inputs. What are the input variables? We have to pass the query token IDs. We have to pass all response and episode advantages, and it's gonna be torch dot. I think we can just say good. So if we look at the input IDs, so yeah, everything kind of checks out with whatever we had before.
One question. There are sometimes is it if you concatenate these the query token ID and response token ID, and then convert this to text and tokenize it again, it's no guarantee that you will get the same input IDs, right?
There is no guarantee because I think the entire process of tokenization and detokenization, it's not really guaranteed to be.
Is it called invertible? I don't know.
Invertible, yeah.
The F
because there are even from before talking about the tokens and the greedy decoding of these byte pair implementations, I think there are pre-processing steps. For instance, let's imagine that your model has generated 100 spaces for whatever reason. So 100 tokens of spaces. If you feed this to the tokenizer, it's going to convert these, it's going to perform some pre-processing that is going to convert these 100 spaces to maybe 10 very big spaces.
I see. So the generation and the tokenized version are going to be different.
Exactly. So even these kind of small details and intricacies, they're going to make some difference.
So under most of these tokenizers, if you generate from the model and you get a string, and then you de-tokenize it, you may get different input IDs.
There is a possibility.
It's possible.
Yes.
It's completely possible. No guarantee. Interesting. Okay, so we conclude this part.
Yes.
Right? So we now know how to prepare our input to feed to the model, and we also know how to compute the token log probabilities.
Exactly.
So we have all the ingredients for the policy gradient loss.
Exactly. So in the next section, we are going to implement the actual computation of policy gradient.
Finally.
Fine. Okay. Now we want to finally write a function that computes the policy gradient loss so that we can backprop through it and afterward update the model. Okay. And I just copy pasted the terms that we're going to need when we want to compute the loss. As we know, the first term is the Bonino policy gradient with advantage, and the second term is the KL-divergence. If you don't remember this, please pause at this point and relook at all of this definition and why these are in this form from the previous sections of this video. Okay, so I'm gonna define a function, compute policy laws, I guess, and it's going to receive inputs. So it is a dictionary that has the inputs that we are going to feed to the model. And we have computed this in the previous sections. Okay, so it is going to return to us torch tensor. So this is the entire body of this function. This is the definition of this function. Just before doing this, let me load the models into the GPU. So for the policy, we auto model for causal LLM. Oh, I think we made a typo here. From pre-trained, I think we did this before for computing Logprobs, but let's do this again just to make sure. So passing the model name, torch D type is going to be the vFloat 16, and we're going to use the flash attention implementation. I think it was attention implementation, if I'm not mistaken. I hope. Okay, and device map, it's going to be 0. So we are going to load this into first GPU. Okay, let's see what happens. Perfect. We're going to load the same model as our reference policy because we want to compute the KL penalty, and it requires to compute for us to compute the reference log probabilities under for the same episodes.
So currently, you have two models on GPU.
Two models on GPU.
One is policy, one is reference policy.
Exactly. However, we are not going to have any optimizer for the reference. So the optimizer memory usage is just for the policy. Okay, let's go and implement the compute policy loss function. For the first step of implementing this function, I'm gonna just export all of the variables from this dictionary because it is easier to work with. So input IDs is going to be inputs, and in reality, this is these inputs are batch of inputs that are going to be passed to this function. Attention mask equal to inputs. What else we have? Oh, sorry. Labels. So just before going any further, you just want to put the dimensions for this. So all of these, they have batch size as the first dimension, and the second is going to be sequence length. Okay, and don't forget we have an advantage here, and okay, and this is also going to have the same dimension as all of this. Okay, so right now we have this, and we can just easily go and compute the props for the reference and the policy. But before doing that, I want to first compute the labels mask because it's going to become handy for us when we want to ignore the indices where the label is embedded or just the padding tokens. So I want to compute label mask. It's going to be labels. However, we have to remember that we are going to shift the labels one to the left because we have discussed this. Please check the previous section if you are not sure why we are doing this. Okay, so this is going to be your labels, and we are going to only keep the ones that are not minus 100 for the ignore mask, ignore index. And let's convert them to floats. Okay, so yeah, right now we have everything for computing the Logprobs. Okay, so right now I'm first going to compute the Logprob.
One question: don't we do the shifting of the labels inside the compute token Logprobs?
Yes, but right now we want to mask a couple of stuff that
Also here.
terms. Yes, we need also compute it here. So yes, now I want to compute the Logprobs for the reference model. So fortunately, because we are not computing we are not backpropping through it, we can just use torch.nograd environment. So we don't want to store any kind of forward paths for this. If you remember, we had the compute token Logprobs function, and the model it receives is a reference policy, and it's going to receive an input for the input dictionary for the inputs. It's also going to receive a temperature. So just to make sure that we have defined temperature here, I'm gonna put 1.0. Let's use capital letters to note that this is a hyperparameter. And unfortunately, we have to again pack these inputs as dictionary because the compute token Logprob it expects a dictionary. Maybe not the best design pattern, but anyway. Okay, or input IDs again. Attention mask and labels. We are not going to pass the advantage because it's just going to compute. This function is going to compute the Logprobs, not the loss function
Since
probs.
we're aware of advantages.
Exactly. So now that we have the reference Logprobs, let me compute the actual policy Logprobs. I'm not going to prefix it with policy because it is just the actual Logprobs of these episodes. So I'm just going to pass the policy here as we have defined it here. Okay, and okay, I forgot to do this. Passing the model inputs and also the temperature, which is the global variable. And okay, perfect. So we have computed reference Logprobs and the actual Logprobs. So everything is ready to compute these loss terms. And just to make sure that we have these things available, let me copy paste them. Just make sure we can take a look at them when we want to implement this. The first term of this entire loss is the Logprob of the policy times the advantage. Okay, so we're going to implement this policy loss. It's the one that I'm going to name it. This is going to be Logprobs times the advantages. However, one thing that we should note that the optimizer implemented in PyTorch, they are going to minimize the loss always, right? But the policy loss that we compute, the policy gradient, it is gradient ascent. So here we have to multiply this thing by -1, just to make sure this is negative. And so we have this Logprobs times the advantages. We have computed everything. And right now we have to make sure we multiply this by label mask. And because we don't want to have any sort of contribution from the advantages. I think in the compute token Logprobs, we apply the label mask for the Logprobs. So whenever there is a ignore index, we are going to have a Logprob of 0 at those points. So these are not going to have any effect.
So we don't want contributions from the tokens from the query and the padding tokens.
The padding tokens. Exactly.
We just want them from the response.
Exactly. So yes, this is going to be multiplied by the mask. And let me also put their dimension here for readability. So here there is one difference. It is sequence length -1 because these are shifted. Again, If you are not sure why we are shifting them, please make sure to rewatch the previous sections that we had this when we discussed this matter.
But the easy hint is that you don't have labels for the last token, so you need to ignore it.
Yes.
The predictions of the model after the last token, you don't know what comes next, so you cannot do next token like loss calculation.
Exactly. It is how causal language modeling is implemented at the end of the day. Okay, so we have the policy loss. So we have computed this term, and now it's time to compute the KL penalty. So for the KL penalty, we are going to have the ratio between the reference policy and the current policy. These two terms need to be computed first. Okay, so I'm gonna name this reference ratio, and I'm gonna use reference Logprobs minus p's. Okay, so we have this thing, and just remember that this reference ratio that I computed is this term, but when we want to compute this, we have to exponentiate it first. So the K penalty is going to be equal to torch dot exponential of this reference Logprobs and minus reference ratio. Oh, sorry, not the reference Logprob, reference ratio. And it is going to be also subtracted by 1. So let's check that again. This is the exponentiation of the Logprob ratios and the Logprob ratios themselves, and minus 1 at the end. Okay, so again, we are going to multiply this by labels mask, because we don't want to compute any KL for the tokens that are masked. And again, let me put the dimensions here. These are all going to have the same dimensions. Okay, so now we have every ingredient with just the time to compute the final loss term. So the loss is going to be policy loss and plus the KL penalty. And
there's a KL coefficient as well.
Yes,
right?
we have to define it also here. KL coef is going to be equal to 0.001, I think, for the experiment. I don't remember exactly, but I think it was about this number times the KL penalty that we have computed here.
Did we test what happens if we just set it to 0?
I think for GRPO, it kind of diverges for the experiment that we had, but for Wine PPO and PPO, they, I think, also diverge, but at much later point. But again, it's all maybe task dependent, model dependent, so it's not a...
At the end, it's a regularization to keep them all sane, right?
Yes, or in another word,
to...
preventing us to go very far away from reference.
But I think like in this task that we want to really deviate from the pre-trained model,
maybe in this case,
it's better to set it to like low numbers.
Yes. Okay, so our loss is basically a scalar, and there is one final thing. So here we just summed all of the, right now, so sorry, this is still batch size by sequence length -1. So we have to convert them to a single scalar. So the way we do this is to just, we sum this term and divide it by the number of terms that are present in this term, in this loss computation. One way to do this is to basically use label mask sum, and this is going to work. However, if you are going to use gradient accumulation, which is going to be the case for us in the actual implementation of this code, let me define this term differently, because we want to divide it by the entire number of response valid labels or valid terms that are contributing to the loss
in the big batch.
In the big batch. And here we have only access to the kind of the mini batch when we are computing the gradient itself. Let's define total responses length. It's going to be int computed from outside of this function. So instead of divided by the label mask, it's going to be divided by the total response length. So yes, and this
There is
is
a disclaimer here, right?
there's a disclaimer which I'm going to talk about in a second. Just make sure everything is performed rightly. Okay, so in general, the reason that we are putting this kind of normalization by the number of all actions or all of the tokens inside the gradient update is that this is a common practice in kind of auto implementation, but if you really want to follow the math exactly, you're going to only divide it by the number of episodes that you're going to use to compute this policy gradient.
Yeah.
But
Just your batch size.
your batch
Not
size,
mini batch size, just the
actual batch size. But this works well. You're going to follow this practice, but if you're not sure what would the effect of using the actual mathematically correct version, feel free to try this at home.
Yeah, it's a great exercise. And yeah, I think it's just convenient to divide the loss by the number of elements that are present in the loss. But
Yes.
it is not from the mass. Like the mass suggests you just divide by the number of trajectories in the loss.
Exactly, because at the end of the day, it is the log-prob of, it is the gradient of log-prob of the entire trajectory.
Which is just a summation, like the summation of the grad log-probs of all the actions.
Exactly.
So you shouldn't divide by the length of a trajectory.
Yes, this is not the average of these terms.
Yeah. It can actually have some interesting effects, like maybe this form incentivizes or disincentivizes long or short responses. We are saying that it's just a common practice, but it does not mean that it's like coming from a very, I don't know, experimented, hard ground truth or something.
Exactly. For instance, you can imagine if you have a very long response and these long responses are going to have higher, like more loss terms inside your loss terms in your gradient computation. In a sense, they have a kind of a relatively bigger role in the gradient, maybe. And I don't know, maybe the model is not going to learn too much about short responses.
Yeah.
Could be one of the effects, but these are really nonlinear functions, so it's not clear what could happen.
That's what you will find out, and please let us know.
Yes.
How should they let us know?
I guess
just write it on Twitter, maybe
on Twitter, on GitHub issues, or even here in the comment section.
In the section, yeah.
Okay, so this is computed. Let me see if I can test this. So imagine that I think we had an episode that we defined in the cells above. Okay, so we're going to have the inputs, prepare model inputs, and I can just copy paste this from here. Perfect. Okay, I have this, and the loss is going to be equal to compute policy loss. So we're going to pass the inputs, and it already has access to the policy and reference from outside of this function. And before that, let me compute the total responses length. And this is going to be equal to all of the response. It is going to be equal to the number of all of the tokens in all of the responses inside these episodes. Okay, so the way we do this is to just say inputs labels not equal to -100, and we're just going to compute the sum of this. And for now, the function expects the float version of it, but it does not really matter when we want to if you want to convert this from torch tensor to Python float. Doesn't make any difference here, just to make sure we are compatible. So let's see. Okay, there's an error. Okay, we have not imported this. Okay. Temperature is not also defined. Okay, this is actually a good point. I forgot to also shift the advantages. So what do I mean by this? Okay, let's look at the shape of the advantages here. What is this? This is byte size times the sequence length. However, if you can see here, we have the Logprobs that are of the shape byte size times sequence length minus 1. And this is exactly as we talked before. These are the shifted labels. And you just need to make sure that our advantages are also aligned to the Logprobs. So this is going to be shifted to 1 to the left as well. Okay, so yeah.
Each advantage of each token is aligned with its actual logprop.
Exactly.
So they are multiplied together, like the advantage of that token and its grad logprop.
Exactly. Right now we have the last term computed. This is a singular scalar, and we can backprop through this. I just want to also print out the KL term here to just make sure. We expect the KL term to be exactly 0 because we have not changed the policy yet at all. KL is equal to KL length penalty sum, and it is going to be divided by the total response length. However, I think for the KL, maybe dividing when you want to report this as an actual KL value, I don't think it should be divided by the number of response length.
It should be, right?
It should be divided by the number of
the episodes, no?
the number of bytes.
I mean, it depends on what you want to see. If you want the actual KL, yes, by the number of episodes. But also, this is a good proxy. The probability over each token differs from the probability of each token under the reference policy.
Yeah, that's a good point. So yeah, any case, you can report both these two numbers. You can check both during the training. Okay, let's run them again. And as you can see, the KL is exactly equal to 0 here. So at this point, we have all of the ingredients that are needed for an RL training, and the rest would be just a simple loop that pull all of these components together, generates the episode using vLLM, compute the advantages, and apply the policy gradient and update your policy. So
we also don't have an optimizer yet, right?
We don't have optimizer yet. In the next section, we are going to implement that. It's time to implement an entire training loop. And just before doing that, we have to make sure that we have defined optimizer, we have defined our vLLM and all of these things together. I know that in this entire notebook, I have defined this and already loaded this to memory, but I want to have all of this in the same block so that it is easy to track and make sure that we know from a bird's eye view what are the stuff that are involved in the training. Okay, so we need to have the reference policy. I'm just gonna go and just copy paste them from here because I think it's better use of the time. So the reference policy would be this one. Okay, and the policy model, it's going to be exactly the same thing. Both these two things are going to be initialized from the initial pre-trained model. And one thing here, we need to enable the gradient checkpointing for the policy model because it's going to help us save memory. Yes, I just copy pasted here because I forgot what was the actual command for enabling gradient checkpointing. But this is a Hugging Face API. If you're not sure what's going on, make sure to check the documentation for Hugging Face. And the next part is going to be us defining the deepest speed module or the deepest speed engine for both of the reference policy and the actual policy. Before doing that, I want to explain why do we need deepest speed exactly. Because in general, deepest speed is associated with multi-node, multi-GPU, sharded training, and so on. So exactly, but the question is that since this is a single GPU training, why do we exactly need deepest speed? Besides all of those sharding mechanisms that we have in deepest speed, for instance, deepest speed 0 stage number 2, there are other optimization that deepest speed has implemented that are going to help us save memory. So one of those particular implementation detail optimization tricks that deepest speed is performing for us is reducing the amount of memory fragmentation. And this is going to help us reduce the memory even more.
But do you know how they do that?
I think the way it is implemented is that they compute the total number of bytes that are required to save the model weight, and they just go and allocate a buffer exactly like a simply like an array of BF16 of that amount, and they copy the tensor like back to back, and they know how to map these exact values to the PyTorch tensors. And they, I think, patch the like policy model or the model implementation. I think this is the actual like detail that's the method that they use. However, these are not really well documented, and I think if you need this, if you need to understand this in more details, please make sure to check out the DeepSpeed engine source code. And I think this is going to be implemented in the zero optimizers class.
One question: it is possible for us even not to use DeepSpeed, right? If we had lots of memory, or
so there are
if we don't care about like memory efficiency.
There are a couple of things to consider. So first of all, we are performing mixed precision training, and in mixed precision training, we need to make sure that we keep track of like the master model weights, and then we want to perform the forward pass. We have to convert them from 32 bits to 16 bits and so on. So there are all of these different components involved in mixed precision training, and I think doing this manually with PyTorch, it's not going to implement that by itself, but I'm not really sure. Maybe in the newer version it performs.
If we didn't want to do mixed precision training, what should we do? Assume we don't want to do mixed precision training.
In mixed precision training, as far as I remember, the Adam optimizer states they are all going to be in full precision, and there's going to be a full copy of the model weights in full precision as well, because once you're updating the model weights from the gradients, I think it is done in full precision mode. And when you want to perform the forward pass, you have to convert the master weight from 32 bits to 16 bits, compute the forward path in 16 bits, compute the gradient in 16 bits as well. And I think that would be the gist of the mixed precision training. And obviously, there are some operation in PyTorch that should be performed in full precision mode. And I think, but those are, I think, automatically handled by PyTorch at this point. But the keeping the master weight, using the master weight to update the weights and so on, I'm not sure whether this is implemented in the PyTorch Adam optimizer. Maybe it is. I'm not sure at this point.
But for flash attention, even we don't have a full precision implementation of it. So it's not possible to do the whole model calculation in full precision, because the kernel for it, as far as I know, is not there, at least for flash attention. If one says, I don't care about mixed precision training, I want to just do the whole calculation in full precision, like the float 32. I think it's not possible.
I think it's not, but I'm not sure at this point whether the 32-bit implementation of flash attention is also available.
Maybe. Okay. So in any case, we are going to do mixed precision training.
Yes, exactly.
And DeepSpeed handles this for us.
DeepSpeed handles this for us beautifully. Yes. Okay, let's import DeepSpeed. And before initializing DeepSpeed engines, we have to copy paste the configs. But let's imagine that the configs are available. I'm going to define it later. Okay, let's initialize the DeepSpeed engines. So the reference policy, we are going to use the same variable names because we're not going to reference this later. It's going to be DeepSpeed initialize. The model is going to be reference policy. And we have to pass the config. But for now, let's imagine that there is a variable defined DeepSpeed reference config. Perfect. But remember that DeepSpeed is going to pass some other variables to us as output, but we are not going to use them. So just keep the reference policy. And the policy model is going to be defined in the exact same way. Let's use DeepSpeed initialization method. Model, policy model again. Config is equal to DeepSpeed config. We will going to define this later. And we have to pass the model parameters because it's actually it's going to hold the optimizers and so on.
So these are the parameters for the optimizer.
Yes, exactly. Parameters. Okay. And before continuing, I want to say why do we use DeepSpeed for the reference model as well. And in the config that we are going to define for the reference model, there is not going to be any optimizer. So this DeepSpeed engine for the optimizer, for the policy, for the reference policy, it's not going to contain any optimization, initialization. However, the reason we do this is that we want to have the same forward pass computation graph as the policy models, so that the computation of KL and everything is just exactly the same. Otherwise, if you were to use the Hugging Face model just to compute the Logprobs reference model, there are going to be really small changes, because I think for the vFlow16, there are some different routes or different modes that are enabled in DeepSpeed. So it's better to keep everything in DeepSpeed engine.
The forward pass would be a little bit different.
A little bit different, yes.
Tiny differences, but
yeah, exactly. I think DeepSpeed is going to wrap the forward pass of Hugging Face transformers model, and so it's going to change a bit. But
it's also nice to have the same API for both models, right?
Yeah, exactly. Yeah, in general, the DeepSpeed, it's not going to change how we talk to the model in sense of passing which variable we're going to pass to the model.
But one question, so currently the reference policy is on GPU, right?
Exactly.
What happens now?
That's a good point. We need to move this to the CPU. So the reference policy here, it is an instance of DeepSpeed engine class. But if you want to access to the actual model, it is the module field or module variable inside the reference policy object. Okay, we just say.
And also one other question. So the reference policy already is taking up some space in the GPU. And DeepSpeed, does it go and free up that, or is it like just going to use the same space? Do you know?
When we move it to CPU?
No, when it's on GPU, like when you initialize it, is it going to?
Oh no, it's not. No, it's not going to add any variable. So the reference policy is already there.
It's not going to create any new tensors.
Yes. However, that's a good question, because for the DeepSpeed initialization of the policy, in the config that we are going to define, we are going to see that we are using the stage 2 of DeepSpeed, although this is a single GPU training. And in that, it is going to define exact same amount of the buffer that is going to create on GPU, on the CPU as well. So it moves the model back to CPU again, create the buffer there, and then copy it back to the GPU. There are some cases where there are not enough CPU memory available, and even initialization of DeepSpeed is going to fail. And it is counterintuitive, because you have available the GPU memory, but you are actually encountering CPU memory error. And this is the exact reason, because DeepSpeed in a stage 2, it is doing some sort of trick behind the scene, and that requires some amount of CPU memory. But for us, I don't think this is going to be an issue. Okay, so we actually moved the reference policy to the CPU, and I think this is done for this part. But let me restart this Jupyter notebook and make sure that all of these things can actually run. Oh, we actually forgot to define DeepSpeed configs.
Oh, that's
so
true.
Yes. Okay, I have copy-pasted all of these variables here, and just to make sure, this is dsconfig. And just quickly, let me go over this configs just to make sure what do they say. For the reference model, we don't really have anything particular. Just the important thing is that we enable BF16. We are going to pass training batch size and micro batch size and gradient accumulation step, but these are just to stop DeepSpeed from complaining. This is in no way is going to be used in any way in DeepSpeed engine for optimization or anything. So for the actual policy, the configuration, it's going to be, again, use DeepSpeed BF16 implementation. That's that. And we have the zero optimization. As I said, we are going to use a stage 2. So we're going to have the overlap communication. I found that sometimes in some versions of DeepSpeed, enabling this or some of the gradient none. Maybe this is going to happen, maybe it's not, but I just wanted to be on the safe side. So the training batch size, the actual training batch size of optimization is the number of episodes per iteration, which for us is going to be 64. And the micro batch size is the per device batch size that we have defined. It is 4. And obviously, the amount of the accumulation step that we are going to perform is going to the division of episode per iteration by the per device batch size. So we're going to have gradient clipping. And here we define the optimizer parameters. So the type is going to be AhaW, although we don't have any weight decay. The learning rate is 1e minus 6, which we have defined above. So these are torch betas and the epsilon. And finally, we are going to enable torch Adam. And this is an important but slightly cryptic thing here. So basically, DeepSpeed, it has multiple implementation of Adam optimizer. The first version is the fuse Adam that it has, where it has some like fuse kernels, and it is, I think, a bit more efficient than normal PyTorch. However, in our experience, we found that this optimizer is a bit, I have to say, unstable.
I think we encountered a very strange error. We were optimizing this 3 billion model. Like, it was working fine on a 1 billion model, and then we started doing it with a 3 billion model, and our experiments were not doing anything, and we found out the model is not changing at all. Like, the parameters were not updated. And the way we knew it was we were monitoring the KL, and the KL was 0.
All the time.
And which was the change. Yeah, we went to great lessons because we never thought of this, and at the end we found out, okay, our optimizer is...
Yes. So for whatever reason, the DeepSpeed internal implementation of Adam, the Fuse version, it's not performing very well, or there is some bug. I don't know exactly what's going on.
Maybe it's fixed now, but
maybe it is fixed at the point
like
that you are
just 1
seeing
month
this
ago?
video. Yes.
1 month ago we were developing this, and at least encountered this with the Quen 2 billion. So if you're seeing the same thing, maybe change it.
Yes. Okay, so yeah, we're just going to tell DeepSpeed, don't use your own internal implementation, use PyTorch implementation, and fine. So we have defined all of these configs. Let's run this cell and see if it works. Oh, we have not run the cell where we define the model name. I think this is defined somewhere here. Okay, here is where we defined the model name. Back to the cell we wanted to run. Okay, torch is not defined. Yeah, so this is the problem with Jupyter notebooks, right? You start and you have to rerun from all of the cells. Okay, so we loaded the checkpoints shard for the reference and policy, but there is also another error. Oh, this is actually one of the intricacies of DeepSpeed. It is expecting a couple of environment variables to be defined. Let me copy paste these environment variables. Okay, these are these environment variables that we have to define. Let's just make sure that OS is imported here. Okay, perfect.
But what are these environment variables?
These environment variables are generally set when we want to do multi-GPU or multi-node training. This master address, it says that what is the rank, the address for the rank 0, what is the port for rank 0, and so on. And generally, when we launch the Python script that has the DeepSpeed implementation and DeepSpeed engine definitions, it expects this variable to exist, and it is used to create a process group among all of the training nodes and training ranks.
So they're all running the same script, but the rank and local rank are different.
Exactly. However, in this case, obviously, it is only a single rank, single GPU, and everything. So we have to define this. Otherwise, DeepSpeed thinks that something else is going on. That's why he expects us to have this package installed, but we don't need it really.
Just let it know that it's a single GPU.
Exactly. I think up to this point, it was successfully run. So we just run the rest of this. Okay, as we can see, it is running nicely. So the first DeepSpeed engine, as you can see, the config is just for the reference model. There is no optimizer here. And the second one, as you can see, everything is defined. We have the AhaMoment. Okay, yes, this one is run. Okay, just to make sure, policy model. Yes, this is a DeepSpeed engine, and there is a module that contains its entire. Okay, so let me clear all of the output, put this back here. Okay, nice and perfect. So just let me take a look at the GPU memory. At this point, we are at 36. And now we need to define vLLM, run the vLLM to also initialize and make sure it has allocated its GPU. So again, I'm not going to rewrite the vLLM definition from scratch. I'm just going to copy this from somewhere here that we defined earlier. Yes, exactly this one. So just going back. Okay, after this, I'm gonna define it here. Let's move this to here. Perfect sampling params. We are not going to use it at this point, but in any case, we need to just, I'm just gonna change this to inference engine because we have LLM doesn't, it's not very informative. It's not a very informative name. And there is an additional variable that we have to define here, enable sleep mode. This is going to be useful for us when we want to tell the vLLM engine to go to a sleep when we are going to perform the gradient computation and gradient like optimization step basically, and then letting it know that it has to come back and reallocate its KV cache on all of its memory. But once all of the training step is done. So this is the algorithm. So we generate the episodes, we put the vLLM into sleep mode.
Which effectively empties the KV cache, so we have memory for the activations.
Exactly. This allocates the entire KV cache, and I think it moves its internal model to CPU as well.
Okay.
And then we perform the gradient computation, like forward pass, backward pass, and computing the KL and everything. Once we compute that, update the model, we re-enable the vLLM engine, update the weights of the internal model inside the internal model of vLLM using the updated weights, and then we go and resample the episodes again.
Nice.
Okay, just let me run this cell as well to just, again, we need to run this. Just give it a couple of seconds. Yep. Okay, done. So we right now have the inference engine as well. I just want to make sure, yes, everything is available for us and ready to go for the actual implementation of the training.
Stay tuned.
I would like to work on an example where we show how this loading of model into vLLM and so on works exactly, and just show how like what is the behavior and why we are doing this. So I have this notebook called vLLM example, which we are going to use to demonstrate this. Okay, let me go over and run this. I'm going to explain it line by line. So we have the imports, nothing really important, and I like use our policy, define it here, and I'm gonna instantiate vLLM. These are the exact same parameters that I used before. Let me run this as well. And just while this is loading, I would like to talk about this function. So we have load model input into vLLM. So why do we do this? There is an internal model inside vLLM. So we have defined a policy here, right? But there is also a copy of a model inside this inference engine. So the job of inference engine is to just perform inference as fast as possible, as quick as possible, and be really efficient with the memory usage. But when we are doing an RL here, we are updating the policy and we are sampling new episodes, new trajectories with the new policy. So we have to update this internal model of vLLM as well to reflect the new policy.
So you just update your model and then the next trajectory should be sampled from the updated model.
Exactly. And Yeah, and the reason, as I said, the reason we do it is that vLLM it doesn't have access to our newly updated policy instance. It doesn't have access to our deepest with NG or any of that. So we have to manually update the internal model.
The very slow way of doing this is you save the Hugging Face model, and then you restart the vLLM using that checkpoint. But this is very slow.
It is very slow. Yes.
So you can actually just load the weights.
Yeah. Yeah, so we have this function here, load model into vLLM. I'm not going to really explain what this exactly do, but this entire expression is to just access the internal model of vLLM, internal classes and objects. Don't worry about this. If you really want to understand this better, please check out the vLLM source code. You can find why we are actually accessing to the vLLM engine, the model inside vLLM engine using these variables. Okay, so this is defined. And in this example, I would like to first sample sample a trajectory from the vLLM engine with the normal policy, with the initial policy. And then I'm going to update the model with some other model and see what happens. Okay, so here we are sampling a response to the hello world query. And as you can see, it's talking about...
Was the first post for this blog, I always...
Yeah, it's talking about a blog post, right? Okay. And everything makes sense because it's a pre-trained model, but yeah. So now I would like to initialize a random model, and in the exact same format of Qwen or the exact same format of the policy that we have, I'm going to load that inside the vLLM engine. Okay, so I'm going to just define the config for the Qwen model. I think we need to also import this. Okay.
The first import, I guess, should be from...
Yes. Sorry. Okay, so we have the config of this model, just looking at this. Yeah. And then I would like to initialize a random model, which is N2 for causal LLM. And we're just passing the config. So this is going to initialize the model from scratch, randomly initialize weights, and just passing to CUDA, moving it to CUDA.
So it has the same architecture as Qwen?
Exactly same architecture.
Random weights.
Random weights. Okay, loaded. And yeah, so we have this thing, random model, random weights, and I would like to load this into vLLM. I'm going to use the handy function that we defined. So just pass random model. As you can see, it is done and it is super fast. So let's copy paste this exact same thing here and see what happens. Yeah, as you can see, this is completely random sequence. So as we expect, this is a randomly initialized weights loaded into vLLM. So this should not really mean anything.
Mix of language and emojis and everything.
Exactly. So this is, I think, uniform over the vocabulary. And right now I would like to load the policy back into vLLM just to make sure that we can generate some sensible responses again. Yes, as you can see, these are much more sensible now. So
so it's a pre-trained model again.
It is a pre-trained model.
And it's also very fast update compared to restarting and saving to disk.
Exactly.
It happens like the loading is just instant.
Yeah. However, I have to note that right now we are in a single process, single GPU setting. Normally, when you have multiple vLLM or multiple inference engines, they are probably located on other GPUs and perhaps on other nodes inside the cluster. And the way to update the weights inside all of these inference engines is to use the Nickel library from NVIDIA. And basically the rank 0 or one of the ranks, it creates a process group with all of these inference engines. And then it broadcasts the weights from, again, rank 0 to all of those inference engines. And this is still very fast, but this is not as fast as here because it is Exactly. We are sharing the memory with vLLM engine, right? We have access to this internal model. But when your vLLM engine is in another computer, in another server, well, obviously you don't have access to its memory. And even if it is, even it is on another process on the same server or same node, you don't have access to its memory. So the only way that we have to update the base is to use the process group and nickel distributed library.
What do you think of recording a video for RL training on multiple nodes?
That's a good point. Actually, maybe we can record a video on TVTU next.
Yes, it's one of the best code bases for RL training, if not the best for academic purposes. Yeah, let us know in the comments if you want us to.
And just a background on what is TreeTune. TreeTune is a smallish library that we developed for our previous project internally. And we actually published it with the paper that we produced using that code base. But we also have another, like a next version of it, which is much more nimble, much more lighter than the original version. And we are using it internally. Maybe if we clean it up, we can release it sometime soon.
Yep.
Here comes the last code part of this video. We are going to implement the actual training loop of R1-Zero like training. And before actually implementing the code, let me go over all of the steps and just to make sure that we know what are the stuff that we do, and also note to myself to just remember all of these steps. So the first step here is to just we sample a batch from dataset uniformly, and once you have these samples, we just feed these to LLM and ask it to generate 4 generations or 4 completion per each of these prompts. And once we have them, we feed them to the episode creation function, and it will convert these to episode, which means that we're going to have the query token IDs, response token ID, and most importantly, their advantages. And once this is done, we put the vLLM or inference engine back to sleep and just free up its memory. Just make sure that we have enough space to run our training. Then we just create these, padded all of these episodes as we discussed earlier. And once these are padded, we pull back the GPU, the reference model back to GPU, because we always put them inside we always put this in CPU to just save the memory whenever possible. And once this is in GPU, we have all of the ingredients to perform our training. So the next part is going to be inside the loop. So this is the gradient accumulation. So we're going to take mini batches from these episodes and compute the loss, take the gradient, store the gradient inside the grad of the weights. And once we have iterated over all of these episodes, we are at the gradient accumulation boundary. So we can actually perform optimization step and update the model weights. One more thing, when we are at the gradient accumulation boundary, it means that we have already computed loss and gradient for the last final step, and we can easily put back the reference model to CPU. It's gonna free up some space for us. Even I think it's going to be around like 6 gigabytes of space available to us. So whenever we want to update the weights and perform the optimization step, we're going to have more memory available to us. And once it's all done, it means that we have updated our policy for one iteration of our RL. And this is the time to wake up the vLLM and update its internal model to use the updated model. Okay.
Great.
So let's actually go and implement this. So I'm not gonna put everything inside the loop first, because I want to implement this for one iteration, and once we make sure that everything is nice and good, then we are going to move this back to inside the for loop and just perform the entire RL loop. Okay, so the first step, as I said, is going to be sampling stuff from our data from our dataset. Okay, we're going to sample a batch of random indices, and once we have those available, we can select samples from the dataset. Okay, so indices is going to be equal to random.choice, and size. So how many examples we are going to sample from the dataset, right? So we have defined this episodes per iteration variable, right? So we know that we are going to use 64 episodes per each RL iteration, RL training group, right? And it means that since we are sampling four completion per each of these prompts, it means that we have to divide the number of episodes per the number of generations to compute the number of samples that we are going to take from the dataset. Okay, so number of samples is going to be equal episodes per iteration divided by generation per sample hyperparameter. Okay, so just taking a look at this, it's going to be 16. Okay, so let's sample this. So the size is equal to the number of samples, and I think the length of this sampling is going to be from the length of our dataset, obviously. So length of our dataset, which is saved in the dataset variable. Let's take a look at this. Yes. So it's going to sample random indices from 0 to this number -1. And we don't want replacement, so we're going to set it to false. Just taking a look at this. So yes, as we can see, we have sampled these examples, these prompts for this iteration of RL. Okay, and so we have these available at our hand. Let's take this, convert these to actual prompts. So there is this select method for Hugging Face datasets where you pass the indices that you want to take from the dataset. Will take you this. So just for us, let's take a look at the first sample. Okay, so yes, as you can see, this is the first example in this batch. Okay, so we have this available, and now this is the time to use vLLM to generate completions. Okay, let's save the output of vLLM inside this gens variable. So we're going to use the inference engine, which we have initialized in the cells above. Use the generate method. And okay, so as I said, we are going to pass the input IDs directly. We are not going to let vLLM tokenize it for us. So because we already have this here. So we use this prompt token IDs argument and pass the input IDs column of this dataset. Okay, so if you want to know what does this mean, it's going to be, input IDs. So yes, it is going to be a list of lists where we have the prompt token IDs. So input IDs. And now I want to pass and control the sampling parameters for this set of prompts. And as we know, we are going to use the sampling param class from vLLM. And basically, the variable, the input argument n controls how many generations we are going to perform per each prompt. The next important parameter is the temperature. And we are not going to use any top P or top K, so I'm just going to pass their default value. So top P equal to 1, it means that we are basically disabling top P. Top K equal to -1, it means that we are disabling top K. And finally, we want to set the max tokens. This is going to be equal to 1024. And finally, we can pass stop token IDs just to make sure that we explicitly say which tokens we want to stop. And this is going to be our end of sentence token ID, which we have computed in the previous cells. So this is the token that we want the vLLM to stop generation when it sees this. And
it does this by the default, right? Or you just want to be explicit?
I think it does this by default, but I just want to be explicit here. Yeah, let's see what would happen here. There is some error here. Oh, I made a spelling error here. Okay. Just waiting a bit. So as you can see, it's already done. It only took 9 seconds. And this is not actually really a slow generation. It's really fast. So only 9 seconds for your generation is actually pretty healthy number. So yes, so we have the generation output from vLLM, but in order to pass this to our episode creation function, we have to convert them to their token IDs and their a list of token IDs and finish reasons. If you don't remember these, you can just go back a bit and see what is the definition of our create training episode function. All generations is going to be we are going to loop over the gens variable. So for gen in gens and for out in gen.output. So basically outputs, I think, yes. And so this output is the actual variable for each individual completion. And we want to take their token IDs, okay? And one thing we have to perform here before going ahead, we have to convert them to a list because by default, this variable returns as a top-up. The final one, all finished reasons equal to list. Let's again copy paste this. Perfect. So yeah, we currently have all of the inputs that we need, which we are going to pass them to or create episode functions. Okay, just to take a look at what does all of this look like. So all generations, sorry, this is a list of output token IDs and all finish reasons. This is stop, length, stop, and so on, right? Okay, so we have this. Now it's the time to compute the episodes. Oh, just looking back at here. So we have sampled this, we have generated the completion, and right now we are just going to create the training episodes, okay? So episode is going to be equal to create training episodes, and we need to pass a batch of samples that we took from the data set. All generations equal to all generations variable here. All finished reasons as well equal to all finished reason variable here. And yeah, we are done. Okay, let's print out some episodes to see how do they look like.
Putting into the model.
This is going to be our query, and we need to use our tokenizer to decode this because everything that we have is in just tokens. So let me just show you what do we have here inside the episode. So we have token IDs for query, we have token IDs for responses, advantages, and we need to just decode the episodes, all query token IDs. The first item, let's use the first item here. Yeah, I think we should be done. Let me just put these symbols to just enclose where the query starts and stops. Okay, so this is this question. And let me copy paste this and...
Actually, you can solve this one.
Okay. So as you can see here, for this example, it is, sorry, the model is using some combination of code and...
At the end, it says that the result is 36 int result.
Yes.
But it's actually a very easy question if you look at it. So you have 39 and you have 77 and 74. So you can make 3 and then subtract it. Becomes 36.
What is the target?
36.
Oh, okay. Yes. Did the model figure this out?
No. Oh, actually? No.
No. Okay. Let's look at one more example and then we can move on.
It's the same question, right?
Same question.
Oh, but this one is like it closes the think token, but starts... Oh, has a more tag. Interesting. It's like it starts a more tag and then...
Yes. Think
Funny.
more. Any case, so these are some examples from the model. We just gonna have this. So now the time is to just put back the vLLM engine into a sleep mode so that it frees up the memory.
Can we see the memory before and after?
Sure. So we have 57, sorry. And inference engine sleep. And we are going to also free up some memory, like force garbage collection and so on. So also sometimes it's good to have some sort of a sleep before doing this. Sometimes it takes some time, and I found it to be a bit helpful to use this sleep before moving on.
What is the one that you're passing to the sleep?
To the sleep, yeah. So vLLM, it has a couple of different sleep modes. So it has a sleep mode 1 and a sleep mode 2. In a sleep mode 2, if I remember correctly, it's going to destroy the model entirely. But I think in a sleep mode...
Oh, 1 is the one you want.
Okay. 1 is the mode that you want. So it's not going to destroy the model entirely, just going to move it to CPU. And we are going to empty cache for CUDA. And I'm not sure whether this is necessary, but let's do this just to make sure we are not getting out of memory errors. Looking back at the memory, yes, 42. So it's about 13 gigabytes.
Yeah, it said 14.
Oh, 15 gigabytes, yes, about 15 gigabytes.
So it really works.
It really works.
Yeah.
Okay, perfect. So I'm just gonna remove this here just to keep it clean. Yep, we have this. So going back to the list, we have completed these parts, and now it's the time to convert these episodes into what the model is going to accept exactly. Fortunately, we have written this handy little function. So I'm gonna define inputs to be prepare model inputs. We have this in the utility file. And if you don't remember how it is implemented, just make sure to check out the previous sections of this video. So the input to this is going to be query token IDs. I'm just going to pass this very quickly. This would have been a great case for Cursor to help us.
Yeah. We snoozed it on purpose.
We snoozed it on purpose.
Because it just goes and copy paste from the actual ground truth code base.
Yes, so this is a notebook that we are completing from scratch for this video, but we obviously have another Jupyter notebook that have all of these things with more details and more tutorial and text, which we are releasing on our GitHub, but Cursor is going to just copy paste those directly, so it's not really helpful for this particular case of this video. That's why we snoozed it. And we have to pass the device to be just CUDA. Okay, just taking a look at this, we have converted this to tensors, stored tensors, and all of these are on GPU. Okay, perfect. So I'm just gonna make sure it is clean. Okay, right now we are going to take the reference model back from CPU to GPU because we're going to perform the gradient accumulation and basically gradient computation for this RL iteration.
The reference model?
The reference model.
Oh, because of the KL.
Because of the KL, yes. So the reference policy, it has as I said, the reference policy itself right now is the deepest bit engine. However, when we want to move it back from CPU to GPU, we have to access the actual PyTorch model using the .module field. So we're gonna say .CUDA, and reference policy also we put it inside in eval mode. We never change it to train mode, but let's make sure that we are explicit about this. Also, our policy model, it has to be in train mode. Perfect. So right now it's the time to go and write the gradient accumulation part of the code. So just before implementing this, let me go over why we are accumulating the gradients. As we said in the previous sections, we are only updating the model, performing single optimization steps per episodes that we take from a vLLM or from our policy, right? And the problem with this is that we have a large number of episodes. We have 64 episodes right now. Maybe you can even increase it to, I don't know, 512 or even 1000 episodes, right? And these episodes, they do not fit entirely in the GPU when you want to compute the data, because the activations for this is going to be quite large. And one technique for this is obviously accumulation. So we are going to take mini batches of these episodes, and for us here, it is going to be mini batches of size 4, and you just compute the gradient on this 4 set of episodes, and just store this gradient inside the gradient variable of the model, and just repeat these steps for the entire set of episodes. And once we have computed the gradient for all of them, we are going to update the model using the accumulated gradient. Okay, this is just a technique to save up memory. Not the save up memory, just being able to update the model on this entire big set.
So DeepSeek is aware of our mini batch size, right?
Yes, exactly, because we have passed it as config here. So it is aware of our
it knows
training byte size, micro byte size, and gradient
accumulation steps.
Perfect. So I'm gonna go over the list of episodes, and take this in sizes of mini batch. Just our mini batch size is going to be equal to a number of episodes that we have per iteration divided by per device byte size. Oh, no, this is not going to be mini bytes. Our mini byte is per device byte size. This is going to be the number of updates that we are going to perform using this mini byte size. So
the number of gradient accumulation steps.
Number of gradient accumulation steps, yes. So yeah, let's go over this. So we're going to go from 0 to episodes per iteration, and we are going to take mini byte size of these episodes. So our mini batch is going to be equal to, and just we're going to take small portions from the model, from the inputs that we have computed here. We're just gonna take mini byte size and chunks from this. Okay, perfect. So we have taken this chunk, and now it's the time to actually compute the loss on this. So loss is going to be equal to compute policy loss that we have defined in the previous sections. So we need to pass the reference policy to this, and the actual policy model or mini batch, and total responses length, which we have to go and define here. So if you don't remember this is going to be the number of all of the tokens in all of the response tokens in this list of episodes that we have. So the way we calculate this is using the label field. We are going to just compute the number of labels that are not equal to minus 100, because minus 100 is the, or in the ignore index, the padding token, padding value. So we're gonna take the sum and items. So let's print this out as well. Okay, let's see. Item. Okay, so we have about 24,000 tokens inside these 64 episodes. Generation in 9 seconds.
So it's like our average is near, a little bit more than 2,000 tokens.
Exactly. So yes, let me pass them here. Perfect. And once we have the loss, we just call the policy model dot backward of loss. So this is the API for performing the backpropping through the policy model using DeepSpeed. So there is one other variable input argument that we have to pass. We want to ask DeepSpeed to do not perform any sort of rescaling of the loss with respect to accumulation. So we have to set this to false. If you want to learn more about this, just look at the documentation for DeepSpeed. And so we have computed the current gradients for this current gradient accumulation step. Now we can just delete the loss because we don't really need it. And so just going back to the list that we have here. So we are exactly here, right? We have the mini batch, we have computed the policy loss, and we have performed the backward computation. So if right now, if you're going to be at the gradient accumulation boundary, we are just, what it means is that we have computed the loss for the last gradient accumulation step, and we don't really need the reference model. So we can easily move it back to CPU to just free up a space for optimization step, right? So we're just gonna use policy model. Again, these are DeepSpeed APIs. Is gradient accumulation boundary. If this happens, we are going to put the reference policy again back to CPU. Okay, and once we are done, we are going to use policy model dot step to ask DeepSpeed to perform one optimization step for us. And so you might wonder why we don't put this inside this if. This if is already handled for inside DeepSpeed, and we have to put this outside of this if to enable DeepSpeed to actually count this number of gradients accumulation.
That's how it knows, right? That you're taking, like, you process one mini batch.
Exactly.
That's how it knows, I see.
So in this step function, it's going to update the policy using the gradient that are already accumulated, and then it's going to also zero grad on all of the gradients. We don't really need to do that ourselves.
I see. So it has no effect, like for the first 15 mini batches, and then at the 16 one, it first zero grad? No, wait. Does it zero grad after it takes the optimization step?
Yes.
I see.
So after the optimization step is done, it also zero graded for us. So yes, this is our entire gradient accumulation steps, and yeah, let's run this and to see what happens. Okay, let's see what happens. So as we are seeing, the KL is going to be 0, and the reason for this is that we have not updated the model yet. Even we are accumulating the gradient, we have not updated it yet. Okay, perfect. So we have actually updated the
model with one gradient.
With one gradient step, exactly. So now it's the time to wake up vLLM
and update the model.
And
that's it.
That's exactly it. Oh, our cursor is back. So we're gonna wake up, and then it's before actually doing the waking up, it's better to make sure that we are okay. We are completing with the help of cursor. Okay, so let's run this. So vLLM engine is back and running. So we have this handy function that's going to accept the policy model and the inference engine to put the new policy inside the inference engine. Okay, and that's basically it.
That's it. One step of our iteration of the training loop.
Exactly.
And you just do it many times, and that's it.
Yeah.
That's the R1 training.
And so we can actually put all of this in a for loop for now to just...
You want to snooze cursor?
Yes, it is annoying here. Cursor tab, snooze for 3 hours. Okay, let's define number of iteration to be 1000, which is the number we're going to use in this example. So I'm just going to copy paste everything that we had from these nodes, and it's going to be lots of copy pasting. We have copy pasted all of the previous steps here, and hopefully it should work, and we should see our training loop.
One step.
As you can see right now, the KL is different because we have already updated the model for one step, so it's a different policy from the reference.
Because it's second gradient update now.
Exactly.
Oh, the kernel crashed for executing the code.
Click here, what happened? Our notebook crashed for strange reasons, and we found that instead of having this garbage collection and emptying of CUDA cache, which we had previously after the wake up of the inference engine, we had to put it before, and that was the issue. And let's run this again to see how it looks like. Oh, we have not defined the temperature. I think I forgot to rerun this cell when I restarted the notebook. Okay, we are sampling the prompts and it's already done. And looking at the output, not a bad response, to be honest.
Yeah,
We have seen
makes sense.
worse. Year 2.
Year 2. It took years.
Okay, so as we saw before, KL is 0 for the first gradient update. We are going into the second iteration. That's great. Sampling only took 12 seconds.
Oh, this sample makes a lot of sense. Do you think a single gradient update improves the model this much? Or are we just lucky?
I think it's good to be hopeful.
Yeah, let's see. Oh.
Waiting. So this is the second iteration and so on. Okay, so we are not going to look at this particular notebook, and instead we have another completely Python script that we can run for this, and I think it's interesting to look at the examples of the model during training. So I'm gonna just run that and continue from this.
Do you want to also explain the training loop in the Python script? Go over it quickly.
I think this is exactly the same as
what we've written so far.
Yes, and just with more logging and computation of metrics,
some
evaluation and so on. But it is basically the same exact thing that we have written here.
It's super close.
So just make sure that we have GPU or GPU memory is free. Okay, let's run the script. So the name of the script is R1 script here, but I think this is going to change in the final repository. I think it's going to be Nano R1 script, but in any case, let me rerun this again.
Or maybe Nano R1, because the script is
implied
there.
Okay. So as we can see, we have a training test split in the script, which we didn't do in the notebook. But yes, as I said, this notebook was just for kind of educational purposes, and this R1 script is more for actual prototyping, working, hacking, and all of this together. And also we have full-fledged Jupyter notebook with all of this tutorial text and everything. If you like Jupyter notebooks, we are going to release both. Okay, so our deepest speed engine for reference is initialized, and we are initializing the deepest speed engine for, this was for the reference. I think we already initialized it for the policy. So we are just waiting for vLLM to load. And let me increase the font size a bit. I think I messed up the... No, that's fine.
Evaluating on test set.
Yes, it's gonna take some time to evaluate on test set because we always evaluate in iteration 0 to just establish a baseline of what is the performance of the model in the pre-train phase, just taking out of pre-training stage. Sometimes it is not 0. It is close to 0, but not exactly
close, right?
0. But I think it's important to see that it is not exactly to 0, because it means that some responses in the distribution of this model actually are good responses with respect to a reward.
They receive some reward. Like, you cannot do training without any reward.
Yes. Our evaluation is done. We are just going for the first iteration. So, okay, this is the first example. This is the query, and these are the response. Actually, this is a quite good looking response.
I forgot to close the think tag, I think, but
yeah, and nothing here.
Yeah, nothing in the answer. But just
yes, we also
we
also report some key metrics here. So as you can see, our format reward is actually 0.2, so not bad actually, quite good.
Is it after one iteration or?
It was in this first iteration, right? Because if you can see, where is the KL penalty is 0, so it means that it's 0. But the equation reward, the actual solving, it is very close to 0. This is the second iteration, and let's see, since we end up with 78. Consistency is close to 78. I might do the trick. Yes,
okay, the KL penalty is non-zero now, and the format reward actually went down. It's still very noisy, so we need to wait.
Yes, it's the variance that you're observing. As you can see, still the format is not really correct, and these are very initial steps of the training. Obviously, the responses are not going to be anything interesting, but we're just going to wait maybe a bit to just show you if we see some interesting stuff. Yes, you can see here, it is writing in some other language or some other alphabets other than English, or this one is pretty bad here. But yeah, this shows that like the language switching phenomena that R1 paper reported. Also, I want to look at here. This is one of the responses, as you can see. Like the think tag, like the format, nothing is really correct, but this way of explaining and talking, I think this is resembling O1 like thinking patterns. So even it is putting out these like new lines, 2 new lines. So I think at the end it's interesting that all of these things, they all exist in the distribution of the model from the very beginning.
You can sample them, and I guess our tuning just maybe recovers them or resurfaces them. I mean,
maybe that's one way of looking at it.
So
still, all of the reports that we see here are 0.
And which iteration are we in now?
I think iteration 3 or 4. In any case, I think we might cut the video to some interesting examples in between. So we are at iteration 10, and as we can see, we already see that the format reward is going up. So this one, it doesn't have any good format, but this one, we have a reward of 0.5. And the reason for that is the model completely figures out when to close the think tag. However, it is putting out a single like an equal sign here. And also this one is not also valid.
Is not great.
Let's see this one. Oh, the reward is 1. Okay, I think this one, yes, beautiful. So yes, the think tag goes perfectly, answer tag, everything is perfect. Format reward 24.
0.24. So the format is being figured out.
Yes. So we are at iteration 12, right? So only after 12 gradient updates.
The format is already being solved.
So it suggests that at least this sort of formatting is easy to figure out.
And 0.27 is going up.
This one is also completely correct. So now that we are at iteration 16, and we stumbled upon a kind of an interesting example here. So first of all, format reward is already at about 40%. It's quite promising. But I think here it shows, I think, resembling planning and also self-reflection, self-verification. So it says that I need to find a pair of numbers, blah, blah, blah. And then it says this is too large. I need to try different combinations. And then
after checking.
Yes. So it says that, yes, after checking here, I find that this equals to this, which is too large. Again,
for another pair, so it's like trying different pairs.
Exactly.
It's already resembling some part of like the thought patterns.
Exactly. But this one, it's not following the format exactly. So it does not get a reward for this. But this concludes the implementation of R1. If you're still with us, congratulations.
Congratulations.
It's been a long video.
It's going to be a long video.
And we hope that you actually managed to learn something from all of this. And this was not the best production quality, but we try to include everything as much as we can in the video. So we try to not miss really anything from all of this entire implementation. I just want to quickly show you how the W&B page of our runs is going to look like, what metrics we plot and what metrics we log, and how to basically track the experiment. So we're going to have two main set of plots. One of them is for the training and the other one is for the evaluation, which we do during the training. So let's look at the training plots. So as you can see, the response length of the model is going from around 500 to almost around 194 tokens, and it is going up. So this is the famous R1-Zero recreation plot that we have seen before, and we have also recreated here with the code base that we showed you. And looking at the equation reward, we are going from 0 to around 60% at the end of the training. And the format reward, interestingly, I think the model completely figures this out around iteration 50. But even as we seen before, even iterations 20 something, the model is very good at figuring out like the format of the response. What else do we have here? So the non-stop rate, it means that on how many portions of the responses that we get from the model didn't manage to even put the end of sentence tag. They didn't stop, the model didn't stop the generation itself. Okay, let's see. And the policy gradient loss, it's not a really meaningful loss to look at. The KL penalty is also one of the values that we can also track. So this KL is after multiplication with the KL coefficient, but the KL itself, it's going to be larger than this. Let's see what else. Entropy, understandably, it reduces during the last iterations of the training, because the model is becoming more deterministic, and at least in the sense that it is converging to this space of responses that are valid to this countdown task. I'm not sure whether we can understand something from the grad norm. Looking at the evaluation plots, so as you can see, at the end of this, we are about 0.6 on equation reward. So it means that we have accuracy of 60%,
which is very good.
Yeah, and response lengths, it also resembles what we saw in the training. And the format reward, there are some fluctuations here and there, but I think at the end of the day, the model is quite perfect at this. So finally, I want to show you one example of the output of this trained model. So here we have like a category episodes, and you can see the episodes generated at each RL iteration, right? Let's open this up. I don't know, let's try to look at some examples. The reward of 2 means that both format reward and equation reward is correct. So this example, the model has completely figured it out. And seems to be an easy example because the model is solving it
but it's also saying try another. Like at first it says this is too high, try another one. And
it is trying, but it's not an extremely hard one. So this one, the model gets it on the first try, which is interesting. But I don't know, let's look at...
Oh, there was, like it says, still wrong, it's incorrect, try, and it's try different things.
Yes, exactly.
It's like the...
So yeah, we also saw these patterns of self-verification, self-reflection very early in the training. So it is not totally
surprising. One time even we see the aha.
Actually said aha.
I think we showed it in the first slides.
Yes. Let's see if we have some more interesting examples here. I want to look at something that is a bit longer. Maybe not this one. We can go to the next page because these are still...
Another try.
I'm gonna look for some incorrect example. Yes, I think this one. So as you can see, the response length is quite high, and the reason for that is just model is trying different solutions, different equations, and they are not really working.
It's still not the answer.
So even at the very end, it says still not. So it's the one that's kind of give up in trying. And I think it just shows that the kind of inference time is scaling, right? So the model is just generating longer and longer responses to
try different
approaches and try to just figure out this problem. But in this case, unfortunately, it didn't figure it out. And this is, I think, the case for all of the responses that we have in this page. So if you can see, you have the reward of 1, and all of these are quite
long responses.
So
it's just a format reward.
Exactly. Okay, so this one is the model. You didn't even finish the think tag. So
it could
1024, which is the max length of our responses. Okay, this sums up, or now that we have the code base complete and working, and we know how it works, we know really what are all the details and where we should change if we want to try some ideas. But speaking of ideas, we have a short list of ideas that just came to us when we were developing this code base. So
we are just low-hanging fruits, right?
Yeah, low-hanging fruits, and I think as a kind of a interesting exploration into the nature of these training runs. And just wanted to also discuss this to, I don't know, warm start some sort of experimentation or idea phase for you.
Yep. The easiest one is to just change the temperature or like the sampling that we do. For example, maybe playing with the KL coefficient. Do we really need the KL coefficient even? Because the pre-trained model is very different from the model that we want to achieve. So maybe you don't need to actually add a reward for it. So, to add a KL coefficient to be close to it. Maybe you need it in the first iterations of a training, and maybe you need to turn it off later so you can experiment with that. You can add discounting factor. So if the reward is at like the end of the trajectory, or if the reward comes in after like a lot of thinking, you discount it. So you reward the shorter thoughts.
Yes, and I think this goes into this behavior that we see with just this GRPO training, that the response length, it's tend to be really long, start to grow. And now the question is that if you have a discounting factor, is the model going to find responses that are more efficient use of its technique tokens, right? So can it actually solve all these questions by being more efficient in terms of test time compute?
Yeah, it's quite possible that it can solve all of them with not that much compute. At least for R1, we know sometimes it finds the answer and it still thinks. Maybe this solves it. Entropy regularization is done in RL for a long time for motivating like exploration. So we added to PPO objectives in order to make the agents explore the environment. Maybe it can help here as well. You can try different models. Does it just emerge with Quen models? Or can we try Llama models?
Yeah.
We should see.
I think there are some evidence. One of the points with all of his idea is that maybe at 2 or 3 months after recording of this video, all of these ideas are tried out.
Yeah,
I don't know. But at the time that we are recording this, there were evidence that it's not really easy or impossible to recreate this kind of R1-Zero like training with Llama models. So now the question is that if it is not possible, then how could we make it possible without kind of injecting pre-training or better data or something like that in that sense?
So like the other one is quantifying reasoning. So we just eyeball it in the responses, but you can try to provide a measure, maybe searching for the keywords and see if it emerges and how the hyperparameters change them if you quantify the reasoning first. You can see the effect of prompt, because in our prompt, we're just saying that you need to keep about it in mind and then let you think it step by step. Maybe you can prompt it differently to incentivize other ways of thinking, maybe, or the effect of prompt on this emergence.
And I would like to mention that the prompt that it was used in all of his experiments, I think it was different from R1-Zero paper. So we are seeing some sort of emergence of this behavior with some other prompts. And the question is that, is there any effect at all?
But this is a prompt we take from the mini R1, is it?
I think this is a prompt we took from mini R1.
Yeah. And you can try a different task. Countdown task is not that interesting at the end, right? Maybe you can try it on your own, the task that you're working on.
I think like other than changing the task, just to make sure that this is like in a more realistic setting. But I think the fact that we started from a pre-trained model and we didn't inject any inductive bias on this run, it's interesting to see what sort of solutions or solution patterns it discovers for other tasks. If you have a kind of a verifiable reward for, I don't know, some sort of a task that is not in math or code, right?
Yeah.
What does the model...
Medical task,
or I don't know, some stuff in law.
It will be interesting. The other thing is, in the countdown task, if you can generalize from 2 to 4, but what does it mean really? Like you train on 3, just the subset that includes just 3 numbers, and evaluate on the subset that like has 4 numbers in it.
Yeah, and sorry, I just wanted to add something to the change task. Like basically with verifiable reward, we can convert any supervised tuning dataset or fine-tuning dataset to verifiable reward, right? So if you have, imagine that you have a sentiment classification, right? So the model has to reason and then predict the sentiment of that tweet or input, right? So what would happen if you train the model with RL using this algorithm, right? And just try it on all sorts of these
multiple choice
tasks,
answerings, right?
Exactly, MNLI, anything really. Does it become better than supervised training?
We guess so. And we have play with reward, like you can play with the reward, maybe give it reward for language consistency, because we see that it speaks in different languages in a single response sometimes. Maybe you can even encourage the actual weight token, like just encourage thinking. Does it? And if you do that, is it going to emerge faster, like the R1 reasoning? The other one is, currently we are assuming online updates always, so we update the model based on the trajectories we gathered once. You can try adding the PPO clipping, so you have offline updates and see the effect of those. I think the current insight is that if you do offline updates, it's worse than online updates.
Maybe. And one question that I have is that what would happen if we don't implement the PPO clip objective and just do
offline
update with the current laws?
Yeah, let's see what happens. Maybe the idea is that it's going to diverge, so maybe that's why we need the PPO clippings, but do we need them? Some papers like Arlu argue we don't, so actually you can just try it out. You can implement Wine PPO. Maybe that's what we need to do. I don't know. But you can implement Wine PPO, Arlu, reinforced and rejection fine-tuning. I think all of them are easy to implement now with this code base. And I think I really like this one. You can change the style, like not just reasoning. Maybe you can incentivize the model to brainstorm first, like you have some brainstorm tags before the ding tags, and then you have the answer tag. So it's brainstorming, thinking, and answering. You can try all different ideas. Maybe you can simulate a discussion between multiple agents. So it's like agent one says this, agent two says this, says that, agent one says that. The final one, maybe do we need reasoning? Or maybe you just ask the model to output the answer.
Yeah, what would happen? How far could you go actually?
How far can you solve it? Is reasoning was actually necessary to get a good evaluation reward at this task? So yeah, I think these are just very low-hanging fruit ideas. You can try way more interesting things.
Obviously, and I think these are just to get people started, really understand this entire like new behavior, new paradigm. And I think even trying like the simplest one would give you a great opportunity to just play with the code base yourself and try to hack it and see where it goes wrong and where it works and where it doesn't.
Yeah.
That's the final part of this video. I would like to go over the GitHub repository that we have for this project. It's called nanoAhaMoment. And here we just have everything that I explained and we went through in this entire video. And just to go over the contents of this repository really quickly, we have the set of instructions, so make sure to follow them. We installed DeepSeek, vLLM, and the flash attention. There are two main parts for this repository, Nano R1, the notebook, and Nano R1, the script. So just opening this up, you're gonna see like a full version of this tutorial and all of this with explanation, text, and examples. And basically, whatever we have gone through in this video, you're gonna see this in this video in this notebook as well. Even with the all of the examples that we discussed and all of the policy gradient slides that we had, they are all repeated here. And you're gonna see these examples as well. This is a kind of full version of this tutorial, and there is a couple of more features in this. There is slightly more features in this notebook, and those are basically loading of checkpoints, logging to W&B, and evaluation, and those kind of boilerplate that we decided to skip for the video.
And also the easy.
So yes, this was the notebook, and let me also open the R1 script. This is the script that contains all of the code inside the notebook. So if you don't want to use Jupyter notebooks for the experiments or larger scale experiments, R1 script is the right implementation for you. Again, I'm not going to go over all of this, but this is the exact same code we saw before with all of these features, checkpointing, evaluation, and everything. So yes, this kind of sums up the entire content of this repository.
I just want to mention that the code is super hackable. So the script.py, I think it can serve as a very good baseline for like academics who want to do research on RL training of LLMs. It's a single file. Every detail is fleshed out as you see. So I think it's a very good base for trying out different ideas quickly. It runs on a single GPU.
Exactly.
I actually don't think anything. Do we have an alternative code base? We discussed it in the other parts, but
yeah, we discussed it early in the video, but I have not seen like something really compact and with all of these details in a single file. I hope this is really helpful for the folks in the research community, and really I hope this kind of starts some exciting research. And if you use this code base, please consider citing us here. We have put the citation here.